Alright, this is my Physics 2211 Lab 3, and this is the one on the black hole. It has two parts. Part 1, the introduction. The purpose was to explore how force and momentum can be split up into parallel and perpendicular components using the star and black hole model, and then using these components to determine the mass of the black hole. The principles we used were the gravitational force, as you can see here. And then also that F net, it was equivalent to the parallel force plus the perpendicular force. Parallel force being equivalent to P hat multiplied D magnitude P over dt, and perpendicular force being equivalent to magnitude of P multiplied by P hat, or dP hat over dt. Alright, as you can see here, you can see my model. The blue line being F net, parallel, orange line F net, and magenta being F net perpendicular. Alright, and the output out every time it was outputting some data was the mass of the black hole at each step, which I then put into a spreadsheet and averaged the mass being 1.32 e to the 34. And then here we were also given our force, which was 8.75516 e to the 28. And you also were given the parallel and perpendicular forces, which when added together would equal F net. Coding, we changed the mass of the star to 2e to the 30, changed delta t, and then we calculated the momentum, just by multiplying the velocity and the star's mass. We used the fundamental principle here, and then we calculated the parallel force and calculated the perpendicular force, and then used Newton's second law to calculate the mass over here of the black hole by rearranging force equation. In conclusion, discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. F net is equivalent to dP dt, and rate of change of P is also equivalent to dP over dt. Mathematically, they are the same, but physically, F net causes dP, or the rate of change, and rate of change does not work the other way around. And they're not the same. They might, mathematically look the same, but they are not physically and visually. Part 2, the goal was to determine the initial velocity needed for a ship to leave the surface of a planet, but also not get sucked into the black hole and crash one way or another. So the force on the planet, Fp, is equivalent to the force of the black hole acting upon the planet plus the force of the ship acting upon the planet. And then the force of the ship is equivalent to the force of the black hole acting on the ship and the force of the planet acting upon the ship. And then we also use Newton's second law and the position update formula to make sure that the planet and spaceship move the model. You can see there. The first line, we changed the mass of the black hole to 1.32 e to the 34, which was observed and calculated in part 1. Modified the ship speed, and then here we calculated the F net net force of the planet using the F grav principle, and then we added both the force of the ship on the planet and the force of the black hole on the planet to get the force on the planet, and then the net force on the ship was equivalent to the black hole on the ship plus the negative of the ship on the planet, which is equivalent to planet on ship. And then we also use Newton's second law to update the position formula and the velocities and make the ship or planet move. In conclusion of part 2, what is the initial velocity for the ship needed in order to have it enter some kind of orbit around the black hole? Your ship would still not need to crash into the black hole nor crash into the planet. So here you would have to calculate both components. The force, what velocity would need to pull out of the force of the planet, but also pull into the orbit of the black hole without being pulled in so far that it crashes. which is different than what we did initially. We have to calculate respectively for each the planet and the black hole.